Hey, hey, it's Dr. J. Probability part 2 today. We're going to start off with throwing a die. So we have one die. It's a 6-sided die. Classic 6-sided die. And we'll just ask some basic probability questions similar to what we were doing with the coin, but we're going to have a lot more possibilities. Obviously, a coin has 2 sides and the die has 6 sides. So we'll ask a series of questions. We'll start with a simple one. What is the probability of obtaining a 5? Of course, on a single throw. I think that's obvious. I'm only going to throw the die one time. Okay? Now, just to demonstrate the event and the formula for probability, we have an event E. E would be obtaining a 5. There's only one side of the die that has a 5. Where's the 5? Oh, there it is. There we go. I had the wrong one. So there's our 5 right there. That's what we're trying to get. That's our event. The sample space. Sample space S is all possible outcomes. So we have 6 possible outcomes. There's only one. There's only one 5 on the die. There are 6 possibilities in the sample space. So you probably could have done this with mental math. The probability of rolling a 5 is 1/6. Or you could sometimes say 1 out of 6. It doesn't matter that it was a 5. Yeah, so in general, on a single die, the probability of any number on a single throw is always 1/6. Because if we're having a single number on a single die and a single throw, there's only one outcome out of 6 possibilities, so it will always be 1/6. So we're going to have to ask some more interesting questions than just a single number on a single throw. What is the probability that the number is odd? Again, on a single throw. Single die. So this time our event, we have 1, 3, and 5. So the number of outcomes, desired outcomes, is 3. There are 3 possibilities. And again, the sample space is everybody. 1, 2, 3, 4, 5, and 6. So the size of the sample space is 6. So the probability of this event taking place. The number is odd as our event is 3/6. You always have to reduce if possible. So 1/2. Which essentially means mathematically throwing a die and obtaining an odd number has the same probability as a coin flip. Because you can kind of think of a die as a coin where you have 3 odds and 3 evens. And so the odds are the same, that you would get an odd number versus an even number. There's an equal likelihood, equally likely that you would get an odd number versus an even number. At some point, we're going to have to use 2 dice, a pair of dice. We'll get to that in a minute. I need a little more vocabulary so that we can enrich the subject a little bit and get some more complicated outcomes. So we're going to define the complement of an event E is written E prime, just like we did in set theory notation. Although back in set theory, we had several notations for complement. In probability theory, it's pretty exclusively using the prime symbol. It's written E prime, and it means that the event did not occur. You can kind of go back to set theory, and you have your E is the event occurring. E prime is the event did not occur. So it's sort of outside of the event space. The universe, this big box, is called S. S is the sample space. It's the entire space, including E and E prime. So the sample space is the union of the event and its complement. So if you unite these two together, you get the entire sample space. So either the event occurs or the event does not occur. We call that the complement. And so we can use our probability formula. The probability of the event not occurring, so E complement, is 1 minus the probability that the event does occur. I used up all my space for my next example. I'm going to have to erase this diagram here. So example 3, what is the probability that the result of a single throw is not 3? So what's the probability of not rolling a 3? Maybe there's something you do not want to roll a 3. Please don't roll a 3. Yeah. So this is our event would actually be rolling a 3. Yeah. We already know the probability of that event is 1/6 from our previous generalization that every number has an equal likely chance of occurring. So rolling a 3, 1/6 automatically. So not rolling a 3, the probability of not rolling a 3 would be 1 minus 1/6, which is 5/6. So you have a 5 out of 6 chance of not rolling a 3. It seems kind of intuitive if you've ever played with a die for a few minutes and roll it around and see the different possibilities, that there are 5 possibilities that are not a 3. So it wouldn't take you very long to figure that one out. Well, eventually we're going to play something similar to craps. Although we're not going to play the actual game of craps because I don't have a crap board. But we're going to just discuss the possibilities of rolling 2 dice at the same time. So next we're going to talk about 2 dice. The sample space gets a lot larger. The sample space, S, is every possibility for 2 dice. Now we're going to use a notation. We're going to use the XY notation. It looks kind of like an ordered pair. So X would be the first die, and Y would be the second die. And we're going to list out all the possibilities so that we get an idea of the sample space of rolling a pair of dice. Okay. So I'm not going to sit here and roll every single possibility. We're just going to use a little mathematical generalization. The sample space, I could get a pair of 1s. I could get a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, and a 1 and a 6. So there are 6 possibilities if the first die rolls a 1. Well, the first die could roll a 2. And there are 6 possibilities for that. So this would be the first die rolls a 2, and the second die rolls a 1, and all the different possibilities all the way to a 2 and a 6. In the camera, you're seeing other sides that I'm not seeing. I'm looking only at the top number on the pair of die. Well, the first die could be a 3, and we could have a 3-1, a 3-2, 3-3, 3-4, 3-5, and of course 3-6. Hopefully you all see the pattern. It's going to be 6 rows and 6 columns. And this will give us our sample space for a pair of dice. So once we have the sample space, now we can look at the different possibilities. So these are the possibilities, the size of the sample space, the cardinality, the number of possibilities is 36 possibilities. There are 36 possible outcomes. Unfortunately, my list of possibilities takes up the entire board. I don't have any room to do my example. So take a quick snap of this, or you can look it up in the homework. I put a chart that shows all of these possibilities so that you can reference them when you're doing the problems. If we need this again, I might have to drum it up again, but we'll see what we can do just from memory. So example 4. What is the probability that the sum is odd? And again, 2 dice, a pair of dice. 1 throw. Now, even though I'm calling it 1 throw, I'll get into this in a minute, it turns out that throwing 2 dice at the same time is the same as throwing 1 die and then throwing the other die. And we'll get into why the probability is the same either way. But in this particular example, I'm just going to assume that these dice are somehow in a cup or something, or in my hand, and I'm throwing them at exactly the same time. So what is the probability that the sum is odd? All right. We already know the size of the sample space, so we'll just hang on to that. We got 36. So the event is the sum is odd. So how many possibilities out of that big list that I erased have an odd sum? One and 1? No. 1 and 2? 1 and 2 is odd. 2 and 1 is odd. So these are actually different outcomes. This means the first die was a 1 and the second die was a 2. This means the first die was a 2 and the second die was a 1. It's one of the reasons why we have the color to distinguish between the two. Okay. Even without the color, you still have these 2 possible outcomes. It's just harder to see which one's which. You could roll let's do all the ones with a 1. So if you have a 1, then the second number must be even in order for it to be odd. So here are all the possibilities where one of the die rolls a 1. So these will all come out to be odd. Now we could do all the possibilities where there's a 2. The first die is a 2. Now we already have 2, 1, so we don't want to use that one again. They have to be different outcomes. So it'd have to be 2, 3 and 3, 2. That's also odd. What else do we have? The first die could be a 2. And the second die, well, we already used 3, so we'd have to go with 5. And then 5, 2. And that would be it. That's all of the possibilities that have a 2 for the first or the second die. I wish I just had the chart still. I could just sit there and circle all the ones that have a sum that's odd. My whiteboard's just not big enough. I need a second whiteboard off to the side here. All right, let's go with 3. All right. We already have 3, 2, so we can't use that one again. 3, 3 is not odd, so 3, 4 is odd. So 4, 3 is also odd. What else? 3 and 6, right? Because 3 and 5 would be even, so 3 and 6 is odd. And 6, 3 is also odd. A lot of possibilities for odd. My guess is it's about half, right? Half evens and half odds, but let's count them all up. Let's see. All right, let's go with 4. All right, we already have 4, 1. We can't use it again. We already have 4, 3. We can't use it again. 4, 4 is not odd. 4, 5. That's the only one. And then you could switch the order. 5, 4. All right, let's go to 5. Now we already have 5, 2. 5 and 1 is not odd. 5 and 1 is 6. So we'll go with 5, 3. Nope, that's not odd either. 5, 4. That's not odd. We already have 5, 4. 5, 5 is not odd. So the only one left is 5, 6 and 6, 5. So these are all the possibilities in which it's odd. Let me just count to make sure I got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are 18 possibilities where the sum is odd. There are 36 total possibilities. So the probability of this event is 18 out of 36, which reduces back to 1/2 again. It's semi-instinctual, semi-intuitive. You know, half the numbers are odd, half the numbers are even. So the probability that you would roll a sum that's odd is 1/2. On a pair of dice, what is the probability that the sum is 7? Probability that the sum is 7. So how many ways can you make a 7 using a pair of die? Well, let's go through the obvious ones. 1 and 6. Of course, 6 and 1. 2 and 5, 5 and 2, 3 and 4, 4 and 3, and that's it. There are only 6 possibilities. So this is our event, and so the size, the cardinality of our event is 6. There are 6 ways to roll a 7. So the probability of rolling a 7 is 6 out of 36, which is 1/6. Interesting. So if you only had one die, yeah, obviously, you can't roll a 7 with a single die because there's only 6 possibilities. But on a single die, every number on one die is equally likely. It's 1 out of 6, 1/6 probability. Yeah. If you have 2 dice, the probability of rolling a 7 is exactly the same as 1 die, the probability of every number. So it's 1 out of 6. The probability is 7. Next thing we're going to do is compound the probabilities. So what's the probability that the sum is 7 and something else? Or what's the probability that the sum is 5 or something else? So we want to form some compound probabilities. So we want to have two events taking place at the same time. Okay. You could use E and F, or A and B, or X and Y. I'm going to use A and B. So A and B are events. I mentioned this in my last video. I cannot always use the letter E. I mean, some people will say this one's E1 and this one's E2 if you really insist on having your events be called E's. I'm open to using other letters, so I'm going to use A and B for my events. Okay. And then S is the sample space. It's the universe, essentially. Okay. So we have several things going on here. Yeah. We have the union. A union B is all of this. Yeah, that's the union. All right, refer you back to the previous chapter on set theory where we talked about the union. It's essentially like a united set. We're uniting the two phenomenon or the two events into one big united event. Okay. So I might want to ask, well, what's the probability of this union? Union is the probability of A or B. Now I got to be careful because there's an overlapping region here called the intersection. If these two events both occur at the same time, that's called the intersection A intersect B. The probability of that occurring, I'm just going to make my universe a little smaller so I have some more room to write. The probability of this occurring would be the probability of A and B. That would be the intersection, and the union, or. Any event that takes place in here, any outcome that takes place in here, would get double counted. So we have the probability of A, we have the probability of B, and so the probability of A or B happening, one or the other, is the probability of A plus the probability of B. So we're going to add these two probabilities together, but then we have to subtract the intersection, because the probability of the intersection, it will be double counted. So we subtract the probability of A and B. You see? Think about it like this. Just think about it in terms of general, set theory. Yeah. If I'm counting these events, these little dots are my events, and I'll be more specific in a minute, although dots kind of correspond to the die. So if I count probability of A, 1, 2, 3, 4, 5, 6, 7, 8, 9, there's 9 occurrences in A. And then I count the probability of B, 1, 2, 3, 4, 5, 6, 7 occurrences of B. And then I add those together, 9 plus 7. So there's 9 in this side, and there's 7 in this side. You would think the total is 16. Yeah? But that's not true. There are not 16 dots here. Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 dots. So 16 is not the correct total. It is not 16. It's 9 plus 7 minus 4, because there are 4 in the intersection, and we don't want to count those 4 twice. So 16 minus 4 is 12 is the total, and that's actually correct. So this formula is very important. When you're calculating a compound inequality, or excuse me, a compound probability, in particular OR, you're going to add the individual probabilities and then subtract the overlapping probability, the one that could possibly be in both. I'll keep this formula up here for our next example. So what is the probability that the sum is 7 and one die is a 1? Okay, and assuming we're still talking about 2 die. So you have 2 events happening at the same time. Okay. So what was that probability? Well, we already talked about the sum is 7, right? We had 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, and 4, 3. So that would be that the sum is 7. And one of the die is 1. So in our event, the probability that the sum is 7 and one of the die is a 1, there are 2 possibilities. So the number, let's be careful about this. So let's call this, the sum is 7. So let's actually write this out. Let A be the sum is 7. Let B be one die is a 1. And so we're just going to calculate this piece right here for now. P and B. We want the probability of P and B. We're not doing the entire formula right now. We're just going to do this piece of it. What's the probability of A and B? Okay. So in order for both of these things to happen, the probability of A and B would be 2 out of a total universe of 36. So that's 1 out of 18. Remember, this is all happening inside of the universe. I could draw out the whole universe. I don't know if it's worth it, but let me just do a truncated version of it. So this is. All right, I'm back. I had to reset the camera. It kept blurring out on me. So we're still here. We're trying to figure out the probability of A and B happening. So our events are A. The sum is 7. So I went ahead while the camera was resetting and filled out all the possibilities where the sum is 7. So 1, 6, 6, 1, 4, 3, 3, 4, 5, 2, and 2, 5. Okay, and then for B, one of the die is 1. So I listed out all the possibilities where one of the die is 1. And then outside of A and B, you have your sample space, which includes A and B, so it's the whole universe. Everything else, I'm not sure if I got them all. 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. What else could we have? We could have 2, 3, 2, 4, 2, 6, etc., etc. I don't really need all these extra commas. Let's get rid of this S here. I want to use that space. We're missing a few possibilities here. What do we have? We should have 36 altogether. Let's see how many we're missing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So we're missing 13 more possibilities. How about 3, 2, 3, 5, 3, 6. That's it for 3. How about 4, 2, 4, 4. We already have it. 4, 5, 4, 6. Okay, I don't want to list them all out. I'm just going to say et cetera, et cetera, et cetera. The size of the universe we already determined is 36. So to sit here and try and write them all down, I'm sure I missed a few, but yeah, I don't want to have to make you watch that. Okay. So we want to know what's the probability of A and B. So the probability of A and B, you can also write it like that, using the intersection symbol for and, is equal to 2. There are 2 possibilities in the overlapping region, divided by the size of the sample space, which is 36. And so that reduces to 1/18. Okay. Now we can answer the bigger question, what is the probability of A or B? You can't answer the or question until you first answered the and question. So to find the probability of A or B, well, that would be the probability of A. So what's A? 1, 2, 3, 4, 5, 6. 6 out of 36. That would be PA. And then PB, the probability of B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So including the overlap, 11, minus the overlap, which is 1/18, but I'm actually going to use 2 36s. It doesn't really matter. You'll get the same answer either way, but you probably remember from basic arithmetic, if everybody has a common denominator, it's going to make your life a lot easier. So 6 plus 11 is 17. 17 minus 2 is 15 out of 36. So reduce this. Those are both divisible by 3. So that'll be 5/12. Excuse me. So we have 2 results here. We have the probability of the and compound, A and B, is 1/18. And the probability of the or, the union, is 5/12. This is sometimes written in the book or maybe in your assignment as AUB. We frequently go back and forth between those notations. Okay. So that ought to do it for the dice problems. We're going to need some more vocabulary. some more terminology before we can play cards. So take one last look at this, and we'll see if I can keep my camera from freaking out on me. So next, we're going to talk about independence. What does it mean to be independent? Two events, A and B, are independent if the probability of A occurring is the same whether or not event B occurs. So, for example, flipping a coin. Yeah. Well, I don't have my coin with me today. I'm not going to get up and go get it, but I put it back in my collection. If I flip a coin, that is independent. So if I flip a coin once and I get a head, and then I flip a coin again and I get a head, those two events were independent. The second probability is the same whether or not the first event occurred had no bearing on the second event actually occurring. Okay? Dice are like that. Dice are independent. So if I have one dice is A and one die is A and the other die is B, the probability of A occurring, in this case, being a 1 or something, is the same whether or not B occurs or not. So dice are independent. Okay. However, cards are typically not. Independent. It depends. The independence of a card game is typically dependent upon whether or not you are replacing the card that you took. So, for example, if I deal you a queen, and then I say, okay, what's the probability that the next card is a queen? Well, if the first card already came out to be a queen, there's one less queen in this deck than there was a minute ago. Okay? So now if the next card, the probability that it's a queen went down because there's one less queen, and then I just keep going and going and going, right? And so each time that I deal another card, what's happening to the sample space? The sample space is getting smaller and smaller, and so it's a non-independent, what we call a dependent probability. Unless you do this. So cards are independent if the card drawn is then replaced. Okay, this is called with replacement. That's the only way that a card game could be independent, or the events can be independent. I should call these events. The cards themselves are just cards, but card events are independent only with replacement. So if I say, okay, you drew a queen. If I put the card back in the deck and then I calculate the probability, well, it will be independent because I'm putting the card back every time. They are dependent if the card drawn is not replaced. So this is what's called without replacement. This is the most common. And when you go to a casino or you play a game of cards, most card games you don't hand out the cards and then put them all back in the next hand. I mean, if you put them all back, you're now starting a whole new game. So each time that a card is drawn, it's not put back in the deck and recalculated. So this type of dependency is what we call conditional. A conditional probability is like this. Let A and B be events. We say the probability of A given B. And so this vertical line is read as the word given. So we say the probability of A occurring given that B has already occurred. So this is the notation for a conditional probability. Let's get out the cards and actually play a little card game. So suppose you draw a queen from a standard deck of 52 cards. What's the probability that your next card, your second draw, you would get an ace? So we're going to do this in two different ways. We'll do it one with replacement, and then we'll do it without replacement. So with replacement, this would be independent. So these events are independent. You always have a sample space of 52 cards because you're replacing the card after you draw it. So the sample space continues to remain the size of the sample space. I'm not sure if you can read that, is always equal to 52 if you're talking about an independent event. So in other words, it makes no difference. The probability that I then draw an ace on my second draw, and put the card back in the deck, is independent of the fact that I had just drawn an ace. So the probability of drawing an ace, that would be my event, I'm just writing the word ace, is, well, there are 4 aces in the deck, and there are 52 cards total. So the probability is 1 out of 13, or 1/13. If I do not replace the queen, that would be dependent, or not independent, also known as conditional. And we'll get more into the terminology of conditional and the formula for conditional in my next example. But for this example, we'll just say it's not independent. Yeah. So the probability of drawing an ace, given that I've already drawn a queen, so we sometimes use this vertical line to indicate that it's conditional. So we say, what's the probability of drawing an ace given that I've already drawn a queen? Well, now the sample space is much smaller. Now, it's an ace, so I have 4 aces, but now I only have 51 cards because I've already drawn a queen, so the size of the sample space has shrunk down to 51. 4 over 51 is not reducible, so that would remain as 4 out of 51. Really quickly, let me just embellish you for a moment with a part C. What is the probability of drawing another queen without replacement? I mean, I just can't resist. We already have the problem out here on the board. So obviously, if you've already drawn a queen, there are still 4 aces. But the probability of drawing a queen if you've already drawn a queen, well, without replacement, not only is the sample space gotten smaller, so the sample space only has 51 cards in it, but I'm asking for another queen, and there's only 3 more queens. And this fraction is reducible. It's one of my favorite fractions. 3 goes into 51 17 times. It's one of those fun facts if you want to be the life of your next party, if you ever get to go to a party again. Okay, so next we're going to play some cards. A standard deck of 52 cards. That's what we consider a standard deck of cards. And before we actually do any probabilities with cards, it's good if we just get kind of warmed up with the different possibilities and the different combinations of cards. So how many different 3-card hands can be dealt from a deck of 52? And notice that the order does not matter. So this particular hand, 6, 5, 7, they happen to all be hearts, is independent of the order of the cards. So before calculating any probability, let's just see how many different 3-card hands we could possibly make using a standard deck of cards. My cards are all over the place. How many possibilities is that? So this goes back to chapter 12 when we were talking about the choice function. So this would be choosing from 52, choose 3. So that is 52 factorial divided by 52 minus 3 factorial over times 3 factorial. Remember, you don't actually want to do a 52 factorial. What you want to do is look for the tail. So you have a tail. 52 minus 3 is the tail. That's 49 factorial. So you're only going to go 52, 51, 50, 49. And then now you have your tail. 49 all the way 3, 2, 1. Again, dot, dot, dot means I'm just being lazy and actually being space efficient, so I don't have to write every single one of those. And then down here you have 49, dot, 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 3, 2, 1. That's the 49 factorial. Again, it's 49, 48, 47, 46, so on and so forth. Those tails are going to cross out. So you really only have this. You only have 52 times, so the factorial is gone. You have 52 times 51 times 50. And then you have 3 factorial. So do yourself a favor and simplify the number of steps. So 3 factorial is 321. Some people stop now and plug this into their calculator. I like to go one more step. 3 goes into 51 17 times. And 2 goes into 50 25 times. And you never have to simplify the 1 because every whole number is divisible by 1 or divided by 1. So 52 times 17 times 25 is all you have to do. There are 22,100 different 3-card hands from a standard deck of cards, which kind of explains why I didn't sit here and literally go through every single combination. Okay. I'm not sure why I called that part A. It's just a review of the different combinations. So now that we've seen that, we can start playing around with the actual probability formula. What is the probability that 5 cards will all be hearts? What is the probability that 5 cards will all be hearts? So if I dealt out 5 cards, I didn't get a single heart. That's okay. What's the probability that all 5 of these came out to be hearts? That's pretty funny. I was trying to get hearts, and look what I ended up getting. I ended up getting all clubs. There we go. It's a little bit more random. Notice they definitely did not come out all to be hearts. So what would the probability that all of these be hearts? Not sure how familiar you are with the standard deck of cards, but there are 13 of each suit. So you have hearts, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then you have jack, queen, and king. Those are the hearts. And then you have so on and so forth, the clubs, the diamonds, and the spades. So hearts, diamonds, clubs, and let's see if I can find a spade. There's a spade. So here are the 4 different suits: hearts, clubs, diamonds, and spades. And all of these have the same 13 possibilities. I'm not going to list them all out, etc., etc., etc. An ace acts like a 1, and sometimes it acts like an 11. So you have 13 hearts. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we know that the event that we're looking for in this particular probability is there are 13 possibilities. All right. And I'm going to deal you 5 cards. All right. Well, how many different 5-card possibilities are there? So the sample space, S, is the number of 5-card hands. And the event E is all hearts. Okay? So the size of the event, there are 13 possible hearts to be dealt. 13. Now, how many 5-card hands are there? Well, we're going to need that combination formula. That's going to be 52 cards, choose 5. It's going to be much more than the last example. So that'll be 52 factorial over 52 minus 5 factorial times 5 factorial. So I've got 52 times 51 times 50 times 49 times 48 times 47. That's going to be my tail. 52 minus 5 is 47. So the tails are going to cancel out. And we're just going to have 5, 4, 3, 2, 1. We'll just save that. This is our E here. Our event E is 13 possibilities. So we've got 52 times 51 times 50 times 49 times 48, all divided by 5, 4, 3, 2, 1. I like to simplify this a little bit. 5 goes into 50 10 times. 4 goes into 52 13 times. 3 goes into 51 17 times. And 2 goes into 48. How many times does 2 go into 48? 24 times. So when you actually calculate, you want to do yourself some favor and calculate the smaller values, or you can suffer with the bigger numbers. It's really your choice. So multiplying this out, you get the size of the sample space. The number of 5-card hands is 2,598,960 different possibilities, of which 13 of those are hearts. So the probability of all hearts is 13 over 2,598,960. I don't think that reduces, but we can try. Oh, it does. Interesting. 1 out of 199,920. I was surprised that 13 does actually go into this number 199,000 times. So if you get dealt a 5-card hand and it's all hearts, you have literally beat the odds. It's 1 in 199,000 times that you would get all hearts. Let's see if we can do it. Let's see if we can beat the odds. We're going to shuffle the deck. Shuffle it really good. Let's see if we can get all hearts. It's more fun if you deal them all out and then flip them over. Let's see. No. Can already tell. All right. Well, I didn't think I would get it with such bad odds. 1 out of 199,920.